Really happy to have a chance to come here and talk to you about some interesting opportunities that I see in cloud research. In particular, what I'll talk about is first of all argue that we can that there's good research that can be done to make clouds more trustworthy, and then kind of shift gears and talk about the opportunities that are there once we've made the cloud trustworthy. There's actually a lot we can do so that the cloud can provide new guarantees to users that are difficult to provide in traditional environments. And so I think there's really an opportunity there, and I'm going to try to kind of make the case that this is something that we researchers ought to be looking at. So, we all want to love the cloud, and I'm not going to belabor this point too much with this audience. I think we've all drunk the Kool-Aid, that's why we're here. But there's just this opportunity here that the scale is amazing. That gives us cost efficiencies that are hard to beat. Amazing. When you buy computers by the acre, it really changes the equations on cost and so on. And there's a bunch of qualities that I think you're all familiar with. The ability to do dynamic sizing of things. So you're not just paying for a constant amount of resources that you have to squeeze into, but instead you can buy for a short time some peak amount of resources and use them for just a few minutes or a few hours. This really changes the game. A few months ago, MapR is a company that does consulting on large data, and they set the minute sort record. Where past years the minute sort record had been set with custom equipment, these guys rented a few hundred machines, used them for an hour, got everything set up, ran the experiment. So for a few $1,000s, they're able to do something that in the past took hundreds of thousands of dollars to do. So just amazing opportunities here. There's this disruptive hardware and software stack that's being built out of commodity machines, inexpensive machines with just this kind of cool software to tie them all together, and again, let you do things that you just couldn't do before. So things like the Google File System, MapReduce, Bigtable, Dremel, Amazon's S3. These are all capabilities that we have now that we're just learning how to tap and take advantage of. And then finally, there are disadvantages of operating these things at scale. It's difficult for you or I or a small company to do geographic replication. The cloud, of course, that comes as part of the territory. You also get this opportunity to hire the very best people in the world, right, and to operate things. And so you have world-class operations, design, and security. In fact, recently, Google actually let slip in some of their work, some of the security that they're able to hire, and it's just something that an average user is unable to do. Okay, so the opportunities here are really pretty amazing to leverage that type of stellar expertise. That said, we all have some worries, and the clouds are big things. When they fail, it hits the news, and so people get worried. Anything that can go wrong will, and these things when they do in the cloud, they hit the news, and so. If you start watching the news, every so often you see about new technical vulnerabilities, technical issues that you might worry about, or actual failures of some cloud service or another, and you can't help but worry when you see these things. Now, if we take a step back from these headlines, you can look at these worries, and I kind of put them into three bins. The first is that we're dealing with a complicated distributed system, and that's undeniable. These are big systems, and they can fail in interesting ways. A second worry kind of stems from the fact that these are black box systems, that you don't necessarily as an outsider know exactly how these systems are being built. And then finally, the fact that it's being operated by a third party gives some people pause. Right? You don't know how it's being operated in some details. And so all these things are certainly things that concern people, but it's reasonable to ask how worried we should actually be. Is this something we want to panic about? And if you take a step back and think about this, these are not fundamentally new concerns. Right? If you look at this first question of it being a complicated distributed system, that's true. Right? But so are the on-premises solutions you might be looking at in a lot of these cases. Now, admittedly, when we go to the cloud, multi-tenancy in this scale does make these issues harder in some dimensions. And so there certainly are some new issues. But there's, we've always had something of these issues to deal with. Similarly, if you look at this concern about it being a black box, we don't know exactly how this software operates. Well, that's true, but then it's been true for a long time. If you're using SAP or Oracle, you don't know the details of what's going on inside. Or if you look at metal-wrapped software like EMC gives you, you don't know the details there as well. Yes, it's operated by a third party. That's a new issue, but on the other hand, if you're a large company, you already have your IT being operated by your employees, your contractors, your vendors. It's an illusion that you have absolute control in either of these environments. And so, absolutely, it's reasonable to be cautious. Some of these concerns have shifted. Some of them, I think, are bigger concerns, but these are not entirely new threats. And this should give us some confidence that there is hope to deal with these issues, and that's something we as researchers can contribute to. So as I said, what I want to do today is talk first about how I can stop worrying, and this comes in a couple of fronts. First of all, I should point out that there are some really important non-technical aspects of the cloud that we as researchers don't want to put the tinfoil hat on and forget about. These are not, however, what I'm going to talk about today. What I'm going to talk about today are technical principles that we can apply. I'll talk about two of them. I think, again, as researchers, we want to pull out more of these things that we can push on. I'll talk about end-to-end checks and internal robustness and how we can push those things to make cloud services truly trustworthy. But beyond that, I want to make the case that the cloud brings new opportunities to actually improve the trust that we can provide to services. And so I'll talk as an example of this, and I think this is early stages, but I'll give an example of this, a system called PiBox, which is a platform for trustworthy apps, where we're going to use the cloud to improve the trust that we can deliver to end users. Okay. So just to pause for a second and just remind us all about the research question, or the non-technical issues that do increase cloud trust. And we want to keep these in the back of our mind. These systems have world-class staff, both at the design level, the implementation, operations, security. Some of these companies can hire the best in the world, and that's an important thing to remember. A well-run cloud is going to have good internal controls about who can access data, who can access logs, and when you access that data, it will be logged. You'll be careful about there'll be procedures in place for hiring and firing people, all these things that you've got to do. And adding on to that physical control, taking advantage of geographic replication, so no individual user can easily get to multiple places, physical isolation, and very restricted physical security, as we saw a few slides ago. Okay, and these are all important things. But as I said, what I want to focus on are some of the technical principles that we can apply in this environment. So for my first technical principle, I want to appeal to, I think, really an underappreciated visionary in technology from a couple of decades ago, who told us wisely, "Nol verre, nol proverre," right, which is, as we all know, trust but verify. Right? And so to put that in a little bit less colorful terms in this environment, end-to-end correctness checks are a really powerful idea that we can use in interesting ways. Now, these ideas can be used in kind of two modes. If you're very paranoid about the cloud, you're really worried, you can design cloud services so that an end user, an external user, can treat the system as a black box and get end-to-end guarantees, no matter what's happening inside of that black box. That's a powerful way to use these techniques. I think a more common way that these techniques will be used will be internally by the operator of the cloud. Right? That as you're running the cloud, you want to make sure you're delivering the right services to your customers. You want to catch the bugs before your customers do. You want to correct those bugs as well. And so these techniques also give you a way, as someone that is operating not a black box, but a clear box, but still a complicated distributed system, these end-to-end checks give you some leverage to make sure all the pieces fit together and do what they're intended to do. So I'm going to give a couple examples of how we can use end-to-end checks to get very interesting properties from large-scale, complicated systems. The first one that I want to talk about is a system called Safestore. This is a system that we looked at the question of, okay, I want to use the cloud, I want to store data in the cloud, but the way that these systems might work is that I can put data into this black box. What I get back is some acknowledgement, and okay, I should feel happy that my data is stored. And I can feel happy as long as I trust that the system was designed properly, that there haven't been software failures, configuration failures, hardware failures in unexpected ways, that they're scrubbing latent errors, that they're doing all the things that they should be doing to keep my data safe. So I can trust that. Excuse me. But after when I've put my data into the system, let's say I put my pictures of the baby pictures of my 9-year-old child in there. Are those pictures still there? Are they still safe? Can I trust that they'll be there 20 years from now? And so what we tried to do in Safestore was provide these types of end-to-end guarantees that I could really trust that this black box storage system is doing what it's supposed to do. So what we did in Safestore was we took a user's data and we divided it up among multiple clouds. So you put some of the data in one of each of these clouds, put some redundant data in a third cloud, and when you put the data in, what you get back is a certificate. The cloud promises that it's got your data, a hash of the data that it's stored, and you can look at this certificate and know that the cloud has promised to keep your data. Okay, well, it doesn't quite tell you that they've got your data, but at least they've promised to do it. What we then do is we provide a way that a user can periodically demand an end-to-end proof of storage. All right, so what we're going to do is query the system and get back evidence that I can look at and be confident that, in fact, they have my data and are capable of retrieving it. Now, this has to be really inexpensive. Right? If I just have to go through and read all my data every so often, that's not going to be an affordable thing to do. So we're going to design the system so that you don't have to read all your data to be confident that you could if you wanted to. And so the way this is going to work is that periodically you can put in a challenge. Just pick a random number, pick an object, send those things into the system. And what you get back is, again, a certificate that says, for this challenge on this object, here's a cryptographic hash of the data that I stored for you and the challenge that you gave me. So I get this back. It's been signed by the provider, and I can look at this and say, they promised that they've got my data. But what does that mean? What it means is that they gave me back a pretty random-looking number. And that doesn't really give me that much confidence. All right. So the key thing is that we've designed this system so that it is highly in the cloud provider's best interest to structure things so that I can trust this reply. All right. In particular, we've designed it so that every once in a while, I can do a spot check on this audit. So I can randomly look at this audit and 1% of the time go off to the redundant cloud storage providers, get the corresponding data, reconstruct the original data, and check what that random number should be myself. If both those numbers are good, are the same, then I can feel confident. They've got my data and can restore it and are capable of reading it because they couldn't have produced this number without reading the data. If they don't match, then I can take advantage of the fact that these certificates have been signed by the cloud storage provider. And so I can take these certificates to any third party and prove that they promised to store the data, they claim to have the data, but they actually lied to me. At this point, we have to appeal to non-technical means, things like contracts and so on, to have appropriate penalties so that I can be confident that that the right strategy for them is to never lie when they produce a certificate. And you can structure incentives properly, so that's the right thing to do. And then, if that's true, then I can believe the certificate, and I only have to spot check it occasionally just to keep them honest. So, to kind of summarize this aspect of Safestore, we're able to take this end-to-end check, trust but verify, and get this guarantee that the storage service is currently capable of retrieving my data. So I can sleep well at night knowing that the pictures of my daughter are safe in the cloud. Right. What this actually plays out technically is that this end-to-end check gives me a tight bound on how long it would take to detect a failure of the system. This tight bound depends on whether I believe that the storage server, the cloud storing my data, is rational, right, trying to maximize their own benefit. If so, it's a pretty short bound. Or if they are Byzantine, if they're willing to throw away my data and pay the consequences and lie to me, it takes a little bit longer. But either way, I do get a bound on how long it takes to detect my failure. That gives me a bound on the time to repair a failure. And if you combine that together, then I get extremely high durability, that I can actually measure my durability and be confident that my data can be stored over decades and I can get it back. All right, so those are nice properties. They let me sleep at night for that particular system. But it's just one property, right? What other properties can we provide from this with this type of end-to-end check? So how far can we push this? Right? So Depot was a system that we worked on asking exactly this question. Right? What's the absolute minimal trust we can put into a black box storage system while still getting useful and strong guarantees out of the system? So the model here is that you've got clients storing data into this black box system. I want end-to-end checks. And I want to know that my system is behaving properly and have strong guarantees. If individual nodes fail, if multiple nodes fail, these failures might be simple failures of losing the data or losing a block of the data, or complicated failures of actually changing the data or giving me old versions of the data. I want to go to extremes. I want this to work even if all the devices in the storage system have the same bug, right? And they all corrupt my data in the same way, or they all lose my data in the same way. I still want to be able to, what can I do? Well, maybe in that case, I resort to fetching data out of someone else's cache. And is that cache data stale or fresh? I don't know, but I want to be able to fall back on that perhaps if I can. So I really want to go to the extremes and try to maximize properties with minimal trust. And what we're able to do in Depot is completely eliminate trust for a bunch of interesting correctness properties. So eventual consistency, staleness, dependency preservation. What this says is that the data I get back is the correct data, and it's also the current data. All right, so it's not even giving me some old version of the data. And I can get put availability. When I say that we eliminate trust, what this means is that every node in the system is completely autonomous. That if the node I'm using is correct, then it doesn't matter if every other node in the system fails. This node is enough to give me these properties without assuming anything about another node in the system. Right? For these other kind of liveness properties, if I want to get my data back, someone has to have it. Right? We can't create the data out of nothing, and so, but we get that property. As long as there's one node somewhere in the system that's willing to give me the data, then I can get it back, right? And it's been stored properly. So even if I have to go to some client, they can supply the data out of their cache if they happen to have it, and I still get these correctness properties, right? I'm not at risk of getting the wrong data from some other client in the system. Okay, so these are about as strong properties as we think we can get with about as weak assumptions as we think we can need. So how do we do that? Right? Well, each client and each server is going to keep all the metadata in the system. This is the basic idea. And what that lets you do is operate autonomously. Whenever someone sends you a message, you can check to see if this message is consistent with your view of the world. If it is, you can accept this message. If not, you reject it. Right? Furthermore, we're going to structure things with, this idea of proofs of misbehavior, so that if I can see that someone is sending bad messages, I can construct a proof that they're a faulty node, circulate that around the system and get them evicted so they stop causing confusion. So let me go into just a little more detail of how this works. What we do in Depot is to protect these consistency properties. Every update has metadata associated with it. So here's the update I'm producing. I'm going to tie some metadata to it. And this update has who produced the update, the object that they're updating, the new value for that object, and then a history of what was the state of this node when it applied this update. Okay? As we pass these updates around the system, nodes are going to store the metadata. Right? And so logically, think of this as a node storing the complete history of every update they've ever seen. Right? In practice, we can optimize that. We can do some garbage collection. But logically, every node has a complete history of all the events that it's observed in the system. What that lets you do is local checks. Whenever someone sends you an update, you can check it against your history. If it's consistent with your history, you keep it. When I say consistent with your history, I need two properties. The first is that there are no omissions. All of the events in that update's history must be events that I know about. Right? So you can't skip forward in time. Right? Second, this update must not modify history. You can't go back in time and change the past. Right? So that I see all these events. What this means in practice is that this update is newer than any other prior update by the node. That is, once I've seen an update at time t, if I later someone tries to send me an update that happened earlier, I won't accept that update. And it turns out those two checks are enough for me to build up a good view of what's happening in the world and enforce some strong consistency properties. Now, this sounds first reasonably simple. It sounds like maybe we're done. It turns out we're not. There's one big problem we have to deal with. Right? The problem here is that a faulty node can create what are called forks in the history. All right, so this node is faulty. It has some memory corruption, perhaps. It sends an update to one node with a red history. It sends an update to the other node with the yellow history. Maybe those are two different updates that supposedly happened at the same time because some corruption happened in memory between when I sent one and sent the other. Each of these nodes can look at the update, see that this update is consistent with everything they've seen in the past, and accept it. Right. So this looks like a reasonable update to accept. But we've actually made the problem pretty severely bad in that now this one faulty node has partitioned my system, right? Because any update that this node sends to this node depends on the yellow update. But this node saw the red update. So this new update is not consistent with its history. It has to be rejected, and vice versa. All right, so if we're not careful, a single bit flip in your system on a single node can propagate through the system, partition the nodes from each other. All right, so we don't want that. We have to somehow fix this problem. And so what Depot does is it joins forks for eventual consistency. What we mean by this is we're going to, the histories of forks, we need to bring them together. And the way we do this is we say that we're going to take this faulty node's mistake and convert it into concurrency. Right. So we're going to treat this faulty node as two correct virtual nodes. One of those virtual nodes sent the red update. One of them sent the yellow update. Right. Once we've done that, we can accept that these two updates were created by two different nodes, and so it's okay their histories weren't quite the same. We can bring them together into a causally consistent view of the world. Now, we still have potentially concurrent updates to the same object. We have to reconcile them, but there's a long history of research going back to Coda and Bayou and some other systems about how to deal with concurrent updates in a system like this. All right, so we can then bring together our history into some sensible thing that might have happened in a correct system. We can also evict the faulty node. We've got a proof of misbehavior of two conflicting signed updates. We can evict that node so they can't cause future damage. Okay, so the first principle here was end-to-end checks. And essentially what this let me have was safety, that I can avoid accepting bad things from other nodes, right? Or I can ensure that the system is doing the right thing, that I won't accept bad information. But we also need robustness, right? So we also need liveness. And so that'll be my second principle, robustness. We need to be able to not just reject bad information. We want to design our systems so that they're able to produce good information, right? So we want this to be true despite all those scary headlines and all those bad things that can happen to my system. So can I build these large, complicated systems in ways that give me extreme levels of robustness to match these high levels of safety that we can construct? Well, if you look back at the two examples I've given so far, you saw that I snuck robustness in there as well, right? That in the case of Safestore, we got redundancy by storing the data across multiple clouds so that if I saw a problem, I could go and fix it. In Depot, to get high availability on gets, we stored lots of redundant data across different nodes in the cloud and even potentially across clients. Right. But you might look at this redundancy that we're putting in place and wonder about the cost. Remember, part of the whole motivation for going into the cloud was this, the great economics that it forces. We have to be careful not to lose those as we try to make our cloud more trustworthy. So let me talk for a few moments about a system called Salis, which tried to square this circle. So in particular, what we tried to do is build a robust, scalable, cost-effective block storage system. And we want kind of the scalability and cost-effectiveness of the current state-of-the-art storage systems that you see. So it turns out that we were really able to take the core architecture of kind of this current generation of cluster storage systems, Hbase, Bigtable, and so on, and make some small changes and adapt it to this untrusting environment. So the claim is that I'm going to get similar cost performance to these traditional systems, but try to get similar robustness to a system like Depot, where I still want to provide end-to-end safety. I still want very strong liveness and durability guarantees, but whereas Depot went to an extreme on this and had every single replica in the system keep metadata about every single update, and allowed configurations where you had 5, 10, 20 replicas of the data, if that's how far you want it to go, we don't want to, that does limit your scalability. And so we want to be able to shard our system, but we're still going to, and that is split the metadata and split the data across different nodes. But we still want this extreme guarantee that says, it's not just a majority of nodes need to be correct, but if any single node in a shard is correct, my data is going to remain live and durable. I'll be able to get my data back. Okay, so we're still going to try to really get strong guarantees there. And so the claim is that I can get the sort of the scalability of these systems. And I've given up a little bit of durability and robustness, but not too much. And the conclusion, what I'm going to argue, is that with some care, we can drive the cost of this type of robustness to really quite low levels. So here's how Salis works. The starting point is the kind of current crop of scalable distributed storage systems. We happen to use Hbase on Hadoop's HDFS. But if you kind of look inside of Bigtable as it was published, or if you look inside of Microsoft Azure Store, they're all pretty similar to this basic architecture. And I think these techniques could be adopted to systems like those. Okay. So in these architectures, you've got a bunch of clients, a fast network, and then you shard the data across a bunch of servers. And kind of inside each of these virtual servers, to use, I think it was Bigtable's terminology, you've got a tablet server that kind of maintains the key value store for a subset of your data. It has no persistent state. Instead, it puts its persistent state on a set of redundant storage nodes. So GFS in the case of the Google file system, in the case of Bigtable, HDFS in the case of Hadoop. So in these designs, you have redundancy across the storage nodes, but you don't have redundancy at your tablet server. Right? So a fault there, that is a single point of failure. And so things like this can happen. First of all, a bad write. If there's a memory corruption as you're trying to write things out across these storage servers, you can actually write the wrong data to them, right? And get a single fault to corrupt all your copies. Another possibility is as it's manipulating indices and trying to find the right version of the data, when you read the data, you may not get the right data back if there's the wrong fault there. Okay. So the other thing that as we were building this system occurred to us is we were actually working with a company that does enterprise backup. And they were actually looking for us to build an extremely inexpensive backup system that they could tell their customers that they could really trust. And as we were thinking about this, we're using this Hbase code base. And that was not designed as a really high assurance file system. There's nothing wrong with it, but that wasn't their main goal, right? And boy, as I was kind of looking at these arguments, that was the one that really convinced me. It's like, wow, I don't want to trust that software is correct. I want to have some way end-to-end of making sure that it's going to operate correctly. So we need to deal with this potential single point of failure. So let me zoom in on this virtual storage node, and let's see what we can do. Okay. What we're going to do is take that single point of failure, that single tablet server, and replicate it. All right. Not too surprising, perhaps. So I'm now replicating my tablet servers, not just my storage. Right. And we're going to put a barrier here at my storage nodes and say the only way a storage node should accept a change to the persistent state is if there's unanimous consent by the tablet servers. All right, so all of them have to agree that this is the right thing to do to our persistent state. Okay. Now, you might be worried about unanimous consent. What if one of these nodes does have a fault? Your system has to stop at that point. But in these systems, you've got a sort of separate configuration server, which we can also replicate, that decides who the tablet servers are at any given time. They're stateless, so at any given time, if worse comes to worse, we can shoot these all down, reconfigure the system, bring up another set of tablet servers to get a group that's able to bring in the state and then agree unanimously on any changes you want to make to that state. So the protocol looks like this. The client sends in its update. Each of these tablet servers validates that the client actually wanted to make the update. They then check to make sure it's a sensible update to do. If so, they put a certificate onto the update and hand it to the next one. So you eventually get a set of certificates from each of the tablet servers from the client saying, yes, this is what I wanted to do, and the update itself, which the storage servers are able to check and store the data if it's an appropriate update to make. Okay. Now, a concern is that I started off by saying this was all about driving our costs down, right, to something that's competitive with these well-tuned systems. And I've just taken a bunch of work and I've replicated it multiple times. This seems pretty painful. But what we do is we co-locate. Oops, sorry. We co-locate. I guess my bar showed it. There should be a nice gray bar here. It's not showing up very well. Where we co-locate the. Oh, maybe it'll show up.
I think the projector's a little.
Yeah. Okay. That's fine. So notice that this is one server. What we do is we co-locate the tablet server and the data. So this is all on one physical machine. This is all on one physical machine. This is all on one physical machine. Okay. So by doing that, we've avoided increasing any of our I/O costs. Right? The data still traverses the network once, twice, 3 times to get to 3 storage server replicas. Right? This is a local update. Right? What also happens, we have added a little bit of I/O cost. Right? We're sending these certificates across the network. So there's a little bit of data going across the network, a few extra messages, but these are by design small compared to the objects that we're storing. So ultimately, the extra cost that we're paying is small. Here's an example on a small a 9-server system that we measured. What this shows is the original. Actually, we tuned Hbase to get better performance than the original one did against Salis. The end version is without compaction in these systems. I'll come back to that in a second, which is some additional work they both have to do. But if you just look at the initial writes, the read performance is quite comparable. We do a little bit worse on sequential reads. We do a little bit better on random reads. For sequential writes, we do about 10% worse. Random writes, we do about 10% worse. When you get rid of the cleaning costs, we do about 20% worse. Okay, so a 10% cost on writes, no significant cost on reads. This seems like something that I might be willing to pay in order to get these stronger assurances. But it's actually better than this. Take a step back and think about how writes actually work in these systems. Right? If you're not familiar with Hbase, it looks a lot like Bigtable, which you might be familiar with. So the client does the write to the tablet server. The tablet server sends the data to a first storage server. They pipeline it down to the other storage servers. Okay? But you're not done yet. You've just put the update into a log. What you then need to do is, after a period of time, you take all the updates you've seen recently, sort them, and then write a checkpoint of all the data that you've recently seen. Okay. Finally, every so often, you go back and read the data out of these checkpoints, and then write new checkpoints, having gotten rid of data that's been overwritten. So this is called compaction. Take the big sparse checkpoints, read them, write them into a smaller number of dense checkpoints. And so in these systems, the data crosses the network 6 or more times. Right? 6 times on the initial write of the log and the initial checkpoint, and then perhaps additional times as you compact data forward in time. In Salis, with the active storage, the data crosses the network 3 times. Right? You get the initial write from the client to the other two nodes in the system, but then all of the subsequent rights of the log, so that was the right of the checkpoint, but then the subsequent right of the log, of the checkpoint is a local operation, and cleaning becomes a local operation. Now, doing this local cleaning, you have to make sure that everyone does the same thing. You don't want one node cleaning the data, but the other one doesn't. So again, you need unanimous consent. So we are still sending some unanimous consent, some metadata across the network, but we're keeping those big updates just on the local node. And so when we looked at the measurements in a network-limited configuration, which is much more the environment that we were aiming at, right? We were aiming at a large backup system where we would have nodes with 10 or 20 or 30 disks. And so in these systems, we become network limited. And we measured on a 16-core machine with 10 disks and a 1 gigabit Ethernet. And there, we're seeing throughputs of about double what Hbase did, which kind of tracks the less data that we're having to send across the network. So our initial goal, this is kind of fun, right? Our initial goal was entirely about improving robustness without hurting performance too much. That led us to a design decision to replicate computation. And that actually turned out to be the right one for performance, right? Because it allows us to move the computation to the data rather than the reverse. All right, so we actually got a very nice performance benefit out of this stronger end-to-end guarantee. So we had our cake and got to eat it too. So just to kind of recap, how I learned to stop worrying, there's, as I said, a bunch of non-technical factors, logging, certification, really top people. And then research things that have been applied. I just gave a couple of examples of these types of end-to-end checks. There's been a bunch of work, and this is just a sampling of it. Also a bunch of work on building highly trustworthy services with robustness despite weird faults in the system, and plenty of other work as well. So beyond that, I want to claim that given that we can build trustworthy systems for all these reasons, the proposition here is that there are interesting opportunities to provide useful new properties. A very simple example of this is if you think about a big mail provider like Gmail or I was going to say Hotmail, whatever it's Outlook or something, whatever it's called now. Gmail's spam filter is way better than my department's spam filter. And this is not a knock against, we have some great people in my department. This is not a knock against them, but Gmail has much more scale, right? They can look at many more good and bad messages, which just makes learning a lot easier. They have a lot more resources than my university department, and they have greater expertise, right? In my department, spam filtering and updating the filters is someone's part-time job. I'm guessing at Google and at Microsoft, these are full-time, there's probably a group of people that are working on this full-time, right? And these are probably the best experts in the world. It's not surprising they do a great job at this. So I want to give another example of this. System we built called PiBox, and the idea here was to protect users from apps by leveraging the cloud. In particular, the problem statement here is that apps have access to sensitive information. So I have on my phone, I've got an app that stores my passwords, including my bank account number and password there, because I do the right thing and I have really complicated passwords for those sorts of things. That should make me nervous, right? Because I paid these guys $5. I have no idea who they are, and they've got access to my bank account. Is that the right trade-off? It probably maybe is, but I'm not quite sure. Accessing my email, right? So like Boomerang's a really cool app, but if I'm a CEO of a company, I'm not sure that it's okay for Boomerang to have access to my strategic planning documents. These apps can access my location, which may be sensitive. I actually have this habit of if I'm in a conversation and a great idea occurs to me, I'll dictate it to my phone, and then it'll email to me. And so Dragon, naturally speaking, here's all my best ideas. Now, my ideas may not be worth very much, but if other people do this could be an interesting a channel here that I should be concerned about. There are apps that have my medical concerns. I mean, this is something that it's a little bit of a concern, and particularly, I'm not convinced we've got a great solution today. What do we do today? We show users, kind of give them informed consent at some level. Here's all the things this app can do. And then there's a button, install or cancel. I don't have the site here, but there was a security researcher who basically explained that dialog boxes, people pretty quickly are trained to understand this is the get work done button, right? And so they learned to push this pretty quickly. And so I don't know if you've ever, A, failed to read every one of these things, or B, kind of said, that doesn't seem, I don't know why they need to know my location, but all right. All right, this is, and you know, and we're pretty savvy, and I certainly have to admit to that shortcut. And these apps are coming from thousands of publishers, right? It's not difficult to know which ones are trustworthy and which ones aren't. I actually went back and did some research into the publisher of my password keeping app, and I saw some things that made me feel a little bit better. So maybe I'm okay with that. But I don't want to have to do that with every single app that I make use of. Unfortunately, this is not a completely abstract or theoretical threat. Researchers in our community and others have found problems. Some of these have made the news. Apps don't always treat our information with the care we might expect. So PiBox's idea is that I'm going to trust the platform provider and not these thousands of app publishers. And there's kind of both a non-technical and a technical argument for why that might be a reasonable stance to take. The non-technical argument is that these types of providers have strong incentives to protect the brand, right? That they've got a valuable brand and they're going to work hard to keep it valuable. To put this in stark terms, you know, maybe the publisher of my password keeping app would see a benefit from getting my bank account. Google wouldn't care, right? So it's reasonable on those fronts to have a little more trust here than you'd place here. On the technical side, if you want to kind of get rid of this sort of fluffy side of things, just on a pure technical basis, if you look at just the definition of trust, you have to trust your platform, right? When you've got your phone, they provided the hardware, they provided the operating system. You trust them by definition, right? Trust says that if this thing failed, if this thing is compromised, you lose your privacy, and that's absolutely true. So you have to trust them as a technical matter. So in some ways, if we push our trust from here to here, we're not increasing the trusted computing base. So what we're going to do in PiBox is build a per user, per app sandbox, right? So this means that if I take an app and I dictate or type in sensitive data, I'm okay because that sensitive data can't go out. Now, just building a sandbox is not, yes, we can do that, but I now have a bunch of useless apps, right? There's not a lot that I can do with an app that can't talk to the outside world. And so the art of PiBox, and I don't claim this is a completely solved problem, is to try to think about how we can take this sandboxed app and let it interact with the world in controlled ways. And these are a balance between functionality and privacy. I'm going to claim that we've got evidence that there are reasonable balances to be struck here. I'm not going to claim that we've got the perfect balance yet, and I'd love people to go off and find better ways to do this work. So the first thing we're going to do is, so the first thing we're going to do is we're going to say your sandbox isn't just on your device, it also goes up into the cloud. All right, so the platform is not just the device. The platform provider is also going to provide me with, or provide the app publisher with, a place to run the back end of their app. Right? And the back end is also going to be in a sandbox. So you can think of this as I have a virtual device, part of which is in my hand, part of which is off in the cloud. Right? And I've got to slice through it in both places. We need to now start adding these storage channels. All right, so the first thing we're going to do is add a private vault in the sandbox, and so you can read and write data within the sandbox. Okay, that didn't do a whole lot. Let's do something more. We're going to have a content storage channel so that the app provider, the publisher of the app from outside of the cloud, can push data into a database. Right? And that database can be read by the individual sandboxes. This lets me do things like if I'm a weather app, I can put the current weather into the database. If I'm a shopping app, I can put my price list and my products there. If I'm doing advertising, I can put the new advertisements there. I can do quite a lot with this channel. The second channel is a way to get data out of the cloud. Okay, now it's getting a little bit scary, but we can do this in a controlled way. Right? In particular, what we provide is a privacy-preserving aggregation channel. So every app gets this channel, and it is shared across multiple users as an output-only channel out from the sandboxes to the external world. but it goes through a declassifier operated by the platform. What this declassifier does is it uses techniques from differential privacy to provide strong guarantees on the amount of data that can leak out through this channel. Now, to be clear here, some data can leak out, but we're able to, from the standpoint of the platform, put provable limits on what can leak out. Okay? So it is a compromise, but it's one that we can have some understanding of, at least. Finally, we add a sharing channel so that different sandboxes can send information to one another. In particular, this is per app and per user. And what the platform provides is an authenticated connection so that you know which user you're talking to. And so the platform is providing a notion of identity, and it ensures that if you intend to send data to a particular user, that's the only user that's going to get this update. Okay? So to kind of just show you how this might work, here's my new venture, PinstaChat. It is a social site for sharing pictures about your hobbies. It's going to be big, all right? And you can implement this in this type of platform by updating into the per app content storage, new filters for the photos, new advertisements because we got to pay the bill somehow, and individual sandboxes can see this, can pull in pieces of this. Within the sandboxes, you can share pictures of your hobbies and interests, and know that if I'm sharing information about the things I like to eat, only these users are going to see that. Finally, we can pull some information out. We can maybe put some popularities on the different types of filters that I'm providing so I know what's useful. I can get counts of the number of ads that have been shown as a publisher of the app and continue to improve it. So what we basically have provided in this environment is several different channels, all specialized in ways that allow us to control how information flows through the system. How strong are these guarantees? I'm not going to go into the details. You can go see the paper for that. But kind of the summary is that we can be quite confident and have very strong guarantees about the privacy for apps that use the private vault and the content storage. For apps that use the aggregation, we can still say very precise things, but these precise things say, yes, a little bit of information may leak out, but we can bound it. In the sharing case, our guarantees are weaker. What we guarantee is that the information flows only to the users that you intend to share with, but we're not able to peer inside of that information. And so we have less control over what gets shared. And so in principle, an app could use steganography to send information to your friends. But what they can't do is use these techniques to get their information back to themselves. Okay, so these are reasonable, we argue, guarantees that are better than what you've got today and reasonable. And then the sort of separate question is, can you build apps under this restricted programming model? And we feel like, yeah, under this green category, there's a bunch of things you can do. Some content creation, localization, notification, personalization. Under yellow, you can add things like ad support, feedback, usage statistics, debugging. Under the red, you can do sharing among users. There are some applications, things like social networking, that just don't fit well under this model. But we can do quite a lot. And so, more problems to solve here, but I think there's evidence that we can do interesting things in this environment. So, to kind of summarize, I think we can build clouds with very strong guarantees through the combination of non-technical factors, end-to-end checks, whether you do them internally or externally, and carefully applied robustness in ways that don't give up the good properties of the cloud in terms of its scalability and cost and so on. And once we're able to trust the cloud, they can provide us with new and better protections than we were able to get in the past. And so this can come from both their scale and expertise, things like spam protection, and also the control that they provide, in this case, protecting my privacy from these users' apps. Now, the point of this talk was to encourage you to help on these fronts, that I think there's more that needs to be done, more that can be done, both to help us stop worrying, right? How can we provide end-to-end checks for more and more services, provide stronger guarantees as we build more and more complicated systems? How do we design for extreme robustness without giving up some of the properties that we really want out of these systems? I think there's also an opportunity that I haven't seen as much work on, because it's something of kind of requires us to think about non-technical factors. But are there ways to leverage or better support some of these non-technical factors? Can we make our end-to-end checks include some tie to the logging to know that it's been logged properly, or things like that? So I think there's plenty more to be done on this front. And even more perhaps on the side of leveraging the cloud to provide better properties. I think that there's some interesting opportunities on the front of security, right? I think the cloud, for example, in the same way that it's a better place to do spam protection for emails, it likely is a better place to do malware protection for guests. And there's been some research on this front. So the scale and expertise, it seems like the right place to do this work. I think this idea of trying to provide better privacy is something that feels like it could be an interesting place to continue digging. So I gave you the example of kind of privacy certified apps by controlling the channels between sandboxes. You could go further if you were willing to go inside of the apps, right? So if you look at some of the information flow work, I suspect you can even provide stronger guarantees than what we've provided here. So as I said, I think there's really interesting opportunities on all these fronts, and I look forward to seeing the work from our community on these fronts. So questions?
Privacy topic toward the end with PiBox. I think PiBox is a really nice, interesting architecture. But it seems like you evaded an issue a little bit in your talking about the platform, trusting the platform. Mm-hmm. Because it looks like your architecture depends on not just trusting the mobile device that Google sold me, but I have to trust the mobile device Google sold me and Google's cloud that is holding the private repository, content repository and stuff. Or if it's Apple, I have to trust Apple's cloud too, to make sure that my device's access to this database are really read-only and stuff like that. So, and that seems like a much different thing than just trusting the hardware software provider. Can you kind of expand on that a bit?
Yeah, I think I'd say two things. The first is, if you look at if we look at this just kind of purely from an adversarial view, right? Once someone has your device, they've got you, right? So if we look at this purely adversarially, it's technically we haven't increased the trust very much. On the other hand, I think you're right that there is more code now that we have to trust. So I think that's a perfectly valid thing to point out. When we were looking at PiBox and trying to think about how you might see something like this deployed, I think a key thing is that you can think about the platform. Choose your platform to be someone that you trust. So one way I could imagine this playing out, if the idea were to take off, would be some third party, let's say SunGuard or someone that deals with enterprises, saying that, okay, we're going to build a curated app store, and in this curated app store, we're going to have apps that conform to these things, and their backends are all going to run on, in this case, SunGuard's backend, or whoever you want to trust as your backend provider. Or maybe you do this as an individual enterprise, right? That I am Boeing, and so I will run my own backend servers, and I'll have a curated app store for things that work like this. And so there's absolutely flexibility on what you define as your platform. And so I think so I think there are certainly different ways that you try to use this.
Hello.
Yeah.
Could you elaborate more on this Safestore paper you were talking about? What if when we're comparing our data with what cloud provider has, and it's not matching? So that means they lost this data. What should we do in this case?
Right. So Safestore had three basic principles, and I focused on end-to-end audits as one of them. The other two principles were redundant storage across multiple cloud providers. And so we worked hard to make that an inexpensive thing to do with clever coding and such. And then the third was maybe less relevant here, but having a very restrictive interface so that a bug on my side can't delete my data in the cloud. Okay, so in this case, what you do if there's not a match is you reconstruct the data either from your cache or from the redundant clouds. And you probably also you probably reconstruct it on a different cloud, but that's the redundancy is what you need there.
And regarding Depot, what if the client is buggy? What should we do in this? Like the client, for example, it's outdated. Cloud went to the new version, so the client will reject all the messages and stuff.
Well, so the client and the individual and the internal servers actually run exactly the same protocol, and so this issue would be one throughout your system. That if you do upgrades, you'd have to do them in a backward compatible way. This is a problem that happens in a lot of large scale services that you try to operate. That you've got a bunch of data lying around. You want to do an upgrade. You have to have some plan for bringing the data out of the old epoch into the new epoch. In Depot, probably what we would do on that front is we would use the garbage collection facility that I described. That actually produces a checkpoint that kind of you get unanimous consent that this is the right new checkpoint. And so I think what you would do is you would produce, if you want to go from version 1 of metadata to version 2 of metadata, you'd build a version 1.5 of the software that knows how to read version 1 metadata and produce a checkpoint that has both version 1 and version 2. And then you'd be able to distribute a version 2 that could then just bring you into version 2. So that type of issue comes up certainly, but I don't think it's a new issue for Depot per se.
Right. So my question is a little bit more abstract, and it's more related to this trust thing that you were at some point discussing. And I'm wondering I think this is always a question about the internet and how we trust people. So assume we would kind of require more, proof of ID from people who upload apps and kind of bring it to the level where in the real world, if somebody steals your credit card account, you can sue them. And then the internet, it seems that for some reason this is, I don't know, this is not an option, or it's harder to get around to this if something like this happens. And I'm wondering if we would regulate more, let's say, who can publish an app, what does it actually mean publishing an app? Would it actually increase trust, or would it make the situation better, or would it just kind of act as a barrier to publishing new stuff and creating stuff? So do you think this is a step that we should take at some point, or it's just
Right. So I think there's 2 points there. You made first a good point that in a lot of cases, the technical means alone aren't going to be enough, and we ought to think about how the technical system needs to interact with the legal system, for example. And so that was something that we did in Safestore. We could design our system so that it explicitly had a connection to the contract. Right? So the contract had to have some relationship between the cost of admitting you lost the data versus the cost of being caught lying about it. And then with that cost, we can then go back and make sure the technical system has the appropriate incentives. And so I think that this interaction with the outside world, the legal world and the regulatory world is an important one to keep in mind. And for sure, you could imagine leveraging that in some of these environments, right? You post a bond to put a new app in or something. That said, I think the idea of filtering the app, you actually you don't want to throw away this idea of filtering the apps themselves. And so there are sanity checks that Apple and Google and presumably Amazon do for the apps that go into their app stores. We should keep doing that, of course. I presume that if a publisher today has a record of doing bad things, they get banned from the store. You could absolutely go further, right? At one extreme, we could say that only Apple is going to publish apps for their platform, and that would, absolutely increase, reduce the vulnerability. But most of us would probably say that's not a good choice to make because we've lost so much richness to these apps. So it's a balancing act of how much you want to restrict, consumer choice versus how much you want to provide protection. So, do we have the right balance? I think Apple seems to is a little bit more restrictive than some of the other app stores, and they seem to have done okay. Maybe there's more to be done on that front. But I suspect that it's going to be hard to get. I think we get a lot of benefit from having a really diverse set of people writing these apps, and so I'd be very cautious about throwing that away.
So my question is a little bit abstract too. So as a user, I really want the storage service providers to implement your technologies.
Right.
But could you comment on what are the incentives for them to really do this? Because I think there's no third-party software that can empirically quantify data reliability and trust across different cloud services.
Right. So, so the question was, how do you get these things implemented? And that's an interesting question. In the case of Depot, we actually implemented a version of that protocol called Teapot that runs on Amazon S3 unmodified. So you can get those guarantees out of that system. And I presume it would run, with some tweaks, we could get it to run on other systems. And so we were able to do that without requiring changes to the provider. Some of these other things like getting getting an audit trail out, that's something that if customers demand it and it can be done in an expensive way, you could imagine it appearing. But for sure, business concerns. I get to solve the technical problem. I get to wave my arms about the business concerns, and that's what I have to do on that one.
Thanks.
Thanks. Thank you. Thank you.